Besides his three laws of motion, Newton is also credited with developing the universal law of gravitation. What the universal law of gravitation explains to us is what is the force of gravity that two objects would feel when placed near each other. So if you had a planet, two planets that are some distance apart, and if we know the mass of these two planets, let's call them A and B, and if we know how far apart the planets are from their centers, call it distance D, then we should be able to compute what the force of gravity is between them. And we do that by saying the force of gravity equals the two masses multiplied together divided by how far apart they are squared. That equation is essentially accurate, except that when it was first developed, Newton did not know what the value of 1 Newton would be because the unit of force had not been defined as a Newton yet. And so years after he made this formula, a constant had to be added into it in order to scale it to the right size. And so we also have a large constant, capital letter G, in front there. And capital letter G is always equal to the same thing. And that value is 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. And so that equation there is what we refer to as the universal law of gravitation. And so you might ask, how does this universal law of gravitation relate to circular motion? And that would be a fair question. And this is what we're going to do with it. So let's say you have a planet of some sort. Let's say it's something like the Earth. So here's the Earth. And then orbiting the Earth, let's say you have some sort of satellite. And so here's a satellite out here. Here's a little antenna on top, whatever that would be. So that satellite is going to be orbiting the Earth. Let's move it back a little further. And so maybe we'll know that this satellite, from center to center, is some distance from the Earth, and that distance always has to be from center to center. If they give you from surface to surface, you have to add the radii into that distance. And so here's the distance between the two bodies, and let's say we know that the mass of the satellite is equal to 200 kilograms. The mass of the Earth is 5.98 times 10 to the 24th kilograms. And the question, and the distance apart, let's say, is equal to, is approximately 275 kilometers. And so once you have this, a question might ask you then, what is the orbital speed of the satellite? And so we'd approach this the same way we would approach any question. In orbit, in space, the only force keeping that satellite in orbit around the Earth is the force of gravity. And that force of gravity then must be pointed towards the Earth because, well, that's really all that would make sense. And we also know that in a circle, the net force is center directed. And so we'd say there's a force of gravity pointing inward. And that's really the only force acting on the satellite. And so I could start doing some math, and I could say that the force of gravity equals mass times acceleration. And now we're moving in a circle, so that acceleration is centripetal acceleration. So on the right, I would have mass of the satellite times the speed of the satellite squared divided by the radius or distance of the satellite. So in fact, we're going to start calling that distance just so it's consistent with the gravity equation in this case. And then on this side, I'd have the gravitational constant times the mass of the Earth times the mass of the satellite divided by the separation squared. And I could cancel some things off here if I wanted to. I could say, all right, the mass of the satellite is the same on both sides, and cross off the distance, and then the square over there. And I can end up with, let's go ahead and move this. And so now I can say that the speed equals the square root of the gravitational constant times the mass of the Earth divided by the separation. And then you'd plug in your numbers and you'd be able to find what the value of the speed is. So let's finish that up. Looking for the speed to be equal to the square root of 6.67 times 10 to the negative 11th newtons meters squared times kilograms, or it should be over kilograms squared. And I guess we're going to run out of room here. So let's see if we can't move this. And that's going to be times our 5.98 times 10 to the 24th kilograms divided by, and that separation needs to be in meters, of course, so 275,000 meters. And if you finish that math up, you get about 38,084 meters per second. And so that's how the universal law of gravitation and circular motion work together.